Welcome back. In this video I'm going to talk about matrix multiplication and perhaps a little bit about linear algebra in general. So I'm going to start by running that script, which gives me some matrices. There's M1, 2 rows, 3 columns. There's M2, 3 rows, 2 columns. There's M3, it's the same shape as M1. You may recall that we can add M1 and M3, or maybe you can't recall it, but that's what we can do. And we add every item one by one. That's a valid linear algebra matrix add, no problem there. But if I tried multiplying M1 by M3, well, it wouldn't be a valid matrix multiply anyway, but the answer that I get is obtained by the multiplying every element of M1 by the corresponding element of M3. So 1 times minus 1 is minus 1, 2 times 0 is 0, and so on. That is not matrix multiply. So how do we do matrix multiply? There's 3 ways. np.matmul is a function in Numpy which will take 2 matrices as parameters, and I'm going to use M1 and M3, and I've goofed it up because I can't multiply those. Well, that's good. There's an error message. You can pore over the error message. M1 and M2 are appropriate shapes. Remember that when we multiply matrices, we've got to take the inner products of rows of one by columns of the other, so we have to have the same number of columns in the first matrix as we have rows in the second, which, if you study those ones, is also true the other way around. So matmul M2 and M1 is also valid. The other, or one of the other ways of doing matrix multiplication is to write M1, call the dot method of a Numpy array, and pass in the other matrix that we want to multiply, M1.M2. That works too, likewise M2.M1. But there's another way again, which is the most compact and the one I'm going to use throughout the rest of it, which is to use the at operator, which has been added specially for this purpose. This is a relatively new feature. So I can do M1 at M2, which means multiply. You just have to learn that, think matrix multiply. At least it's not confusing with star. There's no ambiguity here. So M1 at M2 is the same as M1.M2, which is the same as np.matmul M1, M2. So much for matrix multiplication. Straightforward enough if you're comfortable with matrices and the mathematics of matrix multiplication. All you have to do is use that ampersand, that at operator. But where things can get just a little bit confusing is when you're multiplying matrices and vectors. And the reason is because Numpy offers both 1D arrays and 2D matrices, and you can mix them up a little bit in slightly strange ways. So here's 3 entities that I want to look at. I've rerun my script and it's a nice clean world. Let's have a look at them. Nums is a 1D array with 3 items in it. If I ask what the shape of nums is, I discover that it's a tuple with only 1 item, so it's only got 1 dimension. Let's compare that with row. See the difference? Row.shape, it's a 2-dimensional object with 1 row and 3 columns. Note those double square brackets, which were how I constructed it in the first place. Similarly, column was also constructed using double square brackets. Let's look at it. It's quite clear the way it's displayed that it's a column, and if I were to go column.shape, I would get even more confirmation. 3 rows, 1 column. So how do we mix those with matrices in order to do matrix multiplication, matrix by vector? Now, mathematically, this thing, this nums thing, is not actually a 2D matrix at all. You can't multiply that by matrices, but Numpy lets you do some funnies with it. To see what's going on, let's start with row and col, the genuine 2D row vector and column vector, and see what happens. If we look at this picture here to remind us how matrix multiplication works, if I multiply a column vector on the left by a matrix, I must make sure that the number of columns here matches the number of rows there. So if we look at our data and we look at our column vector here has 3 rows, so I need a matrix on the left which has 3 columns. What has 3 columns? Well, M1 has 3 columns. So I should be able to do M1 at col. And indeed I can. So far so good. What else could I use? It looks like I should be able to use M3 as well, M3 at col. But I wouldn't, oops, why doesn't M3 work? Because I typed M2, that's why. So there's the error message you get. M2, it gives you the size 3 is different from size 2 with a rather confusing error message. M3 at col, which is what I meant to type, is the one that should work, and there it is. What about the row? If we look at the row situation, I can multiply a row vector on the right by a matrix. If I have the same number of of rows here as I have columns here. So I should be able to do row at, let's have a look at my options of matrices. I need to have 3 rows. I can't use that, but I should be able to use M2. And again, that works fine. The other 2 won't work. You can try them if you like, they won't work. So now we come back to the tricky one. What about nums? So nums has a shape of 3. It's a 3-item thingy, but it's 1D. So technically I can't use it in this matrix multiplication at all. It isn't a matrix. But Numpy tries to be helpful, and maybe it succeeds, maybe not, you can decide. If I stick it on the left, nums at M, what can I multiply there? I need 3 rows by M2, nums at M2, it works just fine. The result is a 1D array again. So what's actually happened here is that it's decided that since I'm trying to multiply it on the right by a matrix, it had better be treated as a row vector. So nums behaves as a row vector on the left. If I put it on the other side of the matrix, then Numpy again tries to be helpful, and it tries to regard it as a column vector. So in this case, I need to make that one work. I need, as I did before, to have a matrix with 3 rows. So M3 at nums also works. Again, you can do the checking on the arithmetic if you like. So the key message I want you to get out of that is that if I use 1D arrays and try to treat them as vectors, then if I put them on the left of a matrix, they're regarded as a row. If I put them on the right, they're regarded as a column. If you want to be really safe, though, you can always get by with explicit true 2D rows and columns. But actually, this behavior of converting it to a row or column, depending on what side it's on, turns out to work pretty well. Just one last thing to mention in this sequence on linear algebra, when you're transposing matrices, well, you often want to transpose matrices, there's 3 separate ways here. If I've got my column, I can go column.transpose, and I get it converted to a row. Similarly, row.transpose, of course, gets converted to a column. I can also do np.transpose as a sort of function there of the row, and I get the same thing. But the easiest one of all to do is just capital T, and that's the transpose. So the T attribute of a 2D matrix is its transpose. Thanks for watching. Bye.